Hello, today we look at electrolysis. That is, we look at ways we can produce useful chemicals by applying electrical energy, and we also do some calculations based on amounts of current, amounts of charge flowing, and relating that to amounts of chemicals. So, in a nutshell, electrolysis is where we use electrical energy to drive useful chemical reactions. So in that sense, it's the opposite of the electrochemical cells, the galvanic cells that we looked at in chapters 5 and 6. So it's electrical energy that drives the process in all the electrolytic processes. Incidentally, secondary cells, when they're being recharged, are examples of an electrolytic process. Now, these are generally done to drive non-spontaneous reactions, those reactions which slope the wrong way in the electrochemical series. The only way you'll get these to occur is if you drive them with electrical energy. So, this sums up the essential contrast between electrolytic cells and electrochemical cells, the galvanic cells that we've looked at previously. So the thing that drives the process in electrolytic cells is electricity. That determines polarity, etc. The thing that drives the process in electrochemical cells are the chemicals involved. They're what determine what goes on. So in general, electrolytic reactions are non-spontaneous reactions. They require energy to drive them, whereas electrochemical reactions won't occur unless the line slopes the right way in the electrochemical series. So these are driven by electricity. So the power supply pumps electrons into the cathode in order to force reduction to happen, because reduction always occurs at the cathode. Therefore, because the power supply pumps electrons in there, the cathode is negative. Whereas in an electrochemical cell, of course, the chemical reaction is driving the process. The chemical that spews out electrons into the circuit makes the anode negative. So let's start off with a simple example, the electrolysis of sodium chloride. Now, in these sorts of examples, you have to be exceedingly careful as to what state the compounds are in. Now, this one is molten sodium chloride. Molten, of course, just means liquid, just means a very hot liquid form of a substance. So in the case of sodium chloride, you've got to get it to around 850 degrees for it to melt. So when you do have molten sodium chloride, all you've got present in that mixture are sodium ions and chloride ions. So negative electrode, electrons are pumped in, which makes it reduction at the cathode. What is the strongest oxidizing agent? There is only one oxidizing agent here, of course, and that are the sodium ions. And so the sodium ions are going to be reduced to sodium metal. Note the states, liquid. If ever you put in aqueous into one of these equations, you're instantly, because it's so completely wrong, it doesn't matter. Positive electrode, sucking out electrons from the anode. Strongest reducing agent, the only reducing agent are the chloride ions. So chloride ions are oxidized to chlorine gas. Put them together and you're turning sodium chloride into sodium metal and chlorine gas. And sodium chloride is a very stable substance, of course, so it doesn't spontaneously turn into sodium metal and chlorine gas. These most definitely are non-spontaneous chemical reactions. Whole thing changes when we start talking about aqueous sodium chloride. We have water present now, and I'm going to start off using 1 molar. That means that standard conditions, I can use my electrochemical series to predict. So this time we've got a third chemical present, a very important third chemical in electrolysis. So this time, strongest oxidizing agent at the cathode. So we go down the left-hand side, starting at the top. This is something that you should be doing as we speak. Have a look at your electrochemical series, work your way down. What's the first oxidizing agent you get to? It's right down near the bottom. It is water. Water is a stronger oxidizing agent than sodium ions. So water is going to be reduced. We'll get hydrogen gas and hydroxide produced. And what are we going to observe? Well, we've got a gas, of course. We'll see bubbles. We'll see explosive bubbles if we put a flame to them. And hydroxide is, of course, base. We'll see the pH go up. Pumping in electrons makes it the negative terminal. At the anode, strongest reducing agent. Well, there are 2 reducing agents. So we start at the bottom, work our way up. And this time, we get to water as well. So water is below the chloride ion, so water in the first instance will be oxidized. And what do we get? Oxygen and hydrogen ions. So we'll see gas, and the pH will decrease this time. It's the positive electrode as the power supply sucks electrons out. And what's the overall equation when we combine it? Of course, we just get water being split up into hydrogen and oxygen. All the H pluses cancel out with OH minuses from the cathode, and we're left with just the splitting of the water. So we can use our electrochemical series so long as we're dealing with standard conditions. We can use our electrochemical series to predict what will get electrolyzed. The difference with with electrolysis is that almost always something will end up being oxidized and reduced. In predicting reactions in electrochemical situations, galvanic situations, often there will be no reaction. Here, as long as you've got enough volts, there will always be a reaction. So be systematic about it. Carefully list out the chemicals at each electrode, and then use your electrochemical series systematically. So what have we got at the anode? What have we got at the cathode? Well, in this case, we've got the same chemicals at both electrodes. The electrodes we're using are inert, so they're not going to participate in the chemical reactions. So we can ignore those. So we've just got the tin, the bromide, and the water that we know is there because it's a 1 molar solution. Now, be careful here. It's tin 2+. We can tell that from the formula. It's not tin metal, it's not tin 4+, it is tin 2+. Be careful also, it's bromide ions. It's not molecular bromine, it is bromide ions. So be very careful that you've got the correct form of the chemical. So now we're going to identify the strongest oxidizing agent. Start at the top left, work our way down, and what do we get? The first chemical we get to is tin 2. So tin 2 will be reduced to tin metal. The equation exactly as it appears left to right in the electrochemical series. Then we flip over to the other side of the electrochemical series, start at the bottom, work our way up, and we look for the strongest reducing agent. What is the strongest reducing agent? It's tin 2 as well. So this reaction, of course, will go in the reverse direction as to what's in the electrochemical series. Tin 2 will be oxidised to tin 4 plus. One molar solution of magnesium bromide using copper electrodes. So this time we need to be mindful of the fact that we've got an electrode which can react. So let's list the chemicals we've got. We've got the same chemicals at both electrodes, so that makes it a little easier. We've got magnesium ions, we've got bromide ions, we've got water, and we've got our copper from the electrodes. Strongest oxidizing agent, start at the top left, work our way down. What do we get to? Water. Now, you see you've got to go a long way down to get to water, but that's an equation, a half equation that we use really regularly in electrolysis. It's a reaction that occurs really regularly in electrolysis. So if we look below water in the electrochemical series as an oxidizing agent, all of those ions below it will never be reduced in an aqueous solution. So if you've got water present, having a look at that side, the bottom of the left-hand side of the electrochemical series, anything below water won't react if you've got water present. So sodium, magnesium, calcium, lithium, none of those ions will react in aqueous solution, can be reduced in aqueous solution. So that water half equation is one you're going to come across quite a lot. Go across to the other side, what's the strongest reducing agent? Start at the bottom right, work our way up, and we get to copper. The copper anode will be oxidized. So, do those questions, submit them on Google Classroom, and I'll send off the answers. One fairly simple application of electrolysis is electroplating. A lot of those shiny metal objects you see around the place, that shiny coating is actually produced by applying a very thin layer of one metal on the surface of another. So chrome plumbing fittings aren't solid chrome, they're actually mild steel usually with a metallic chromium layer on the surface. That makes them nice and shiny and resistant to corrosion. So you're giving them you're giving objects the desirable property of one metal, but only using a small amount of it. So if we have a look at how a chromium electroplating cell works, it's very simple. We've got the object to be plated being the cathode. So if we've got a steel tap, then we're going to make that the cathode. Reduction is going to occur at the cathode, and we've got chromium 3 ions in our electrolyte. Chromium 3 will be reduced to chromium metal on the surface of the ion tap. At the anode, we've got a lump of chromium metal. That's going to be oxidized. So we'll be producing chromium 3 ions at the anode. Now, it's a very neat way of doing it, because every chromium ion that is taken out of solution by plating it onto the object at the cathode is replaced at the anode by producing another chromium ion. It's like a circular reaction. What's the overall equation for this cell? Well, if we combine these two equations, what are we left with? Absolutely nothing. The reactions cancel out. So You can sort of view it as we're simply moving metal from the anode over to the cathode. So the anode's going to corrode over time, the cathode is going to be plated, going to have deposits on the surface, and all the time the chromium ion concentration of the electrolyte will remain the same. So if you get an electroplating cell set up this way, you'll be asked questions: what happens to the electrolyte concentration? What's the overall equation? If it's an electroplating cell set up with the metal being at the anode and then the same metal being plated at the cathode, then it's just this circular situation. Don't be tricked.